Hello, everybody. Thank you for tuning in to today's exciting webinar. It's entitled Immune Cell Phenotyping, Cell Surface Architecture Informs Disease Biology. We will get the webinar underway in just a couple of minutes as we sort out a couple of last-minute issues backstage so that we can bring you this exciting live presentation. Our guest speaker is Dr. Erdink Sezgin from the Karolinska Institute in Stockholm, Sweden. Following his presentation, Erdinch will be joined by Hannah van Ooyen, Pixelgen Technologies Scientific Affairs Manager. She's also based in Stockholm. We'll have a live Q&A. I hope you'll submit plenty of questions so that we can have a vigorous and productive conversation at the close of Erdink's presentation. So my name is Kevin Davis with Genetic Engineering News. We will get the webinar underway in just a couple of minutes. Please stay tuned. Thanks for your patience. We'll get underway shortly. All right, everybody. Thank you for joining us on this morning's webinar. I'm Kevin Davis, Editorial Director of GEN. Thanks for your patience. Today's webinar is entitled Immune Cell Phenotyping, Cell Surface Architecture Informs Disease Biology. The webinar is brought to you by Pixelgen Technologies. We'll be hearing from them a little bit later in the broadcast. I'm Kevin Davis, GEN's editorial director. As you doubtless know, the biophysical properties of the cell membrane shape the function of immune cells. They provide key insights into chronic disease and immune dysfunction. Measuring membrane order in immune cell populations can reveal functionally distinct cell states and open new avenues for therapeutics. Today's guest speaker, Dr. Erjink Sezgin from the Karolinska Institute in Stockholm, Sweden, will discuss the profiling of plasma membrane order across a dozen or more immune cell subtypes and in health and in patients with long COVID and chronic lymphocytic leukemia, assisted by transcriptomics technology and assays from Pixelgen, which we'll hear more about a little later. Erjink's team has uncovered distinct subsets in differing in cytotoxic potential, migratory capacity, and surface protein organization for biomedical applications. Erdinch leads the CSI Nano, I love that name, the Cell Signaling, Immunity, and Nanoimaging Lab at the Karolinska. His lab works on biophysical principles underlying cellular processes in health and disease. Much of the lab's effort is in developing advanced imaging, chemical biology, and synthetic biology tool sets. Following Erdinch's presentation, which will run about 20-25 minutes, I think, we'll have a quick message from Hannah Van Ooyen, Dr. Hannah Van Ooyen, Pixelgen's Scientific Affairs Manager. She'll have a little bit more information if we can get her slides up, and then she'll join us for the live Q&A. Hannah is also based in Stockholm, just a couple of hundred meters up the road from the Karolinska at Pixelgen's headquarters. Our two guests will join us then for the live Q&A session. We would love to have your questions. Please put them in the chat or the Q&A box during the course of the webinar, and we will get to as many of those questions as we can. All right, enough from me. Again, apologies for the slightly delayed start, but we're here now. Erdinch is ready to get the presentation underway. Erdinch, we're really looking forward to your talk. Over to you.
Thank you so much, Kevin, for the introduction and for inviting me today. I will basically talk about how we try to make sense of cellular signaling from the biophysical angles. If I see my slides. All right, we can go forward. So in my lab, we're working on how cellular fitness is changing generally is a parameter of physical properties of the cell. So if you want to understand a cell, you can always look at the composition of the cell, do all these omics technologies. And then if you do all the omics technologies for a single cell, you would understand exactly what would make up a cell. But this wouldn't be enough to understand the physiological properties of the cells for the reason that is coming up next. So we believe that there are collective properties that you could actually not be able to infer by looking at the composition. If we go to the next slide. So you see in nature, we have all these collective properties that we cannot really understand by looking at individual components because they're emergent properties. They are more than the sum of its components. So in the next slide, we will see a cartoon of cellular complexity. So this is basically what you can see here, very crowded environment, where you have many collective properties. And in the next slide, you will see a picture of a cell membrane. It is very complex. If you think about a single eukaryotic cell membrane, we have many different types of lipids. A single eukaryotic cell membrane have more than hundreds different types, species of lipids. And when they come together, this collectively, they become really a structure with many emergent properties such as stiffness, viscosity, fluidity, charge, and tension. And I'm going to talk about two of these, fluidity and charge, today in the context of cellular signaling. Next slide, please. So in my lab, we are trying to understand what is a healthy and an unhealthy cell in the context of biophysics. And the second question that we ask in the next slide, what are the molecular codes of this biophysical health? And the next question that we ask is what are the function of this heterogeneity of the biophysical, what is the role of this biophysical heterogeneity? And eventually the question that we ask, can we manipulate the function of the cells by manipulating the biophysical properties? So with this, we can go to the next slide, please. I will talk about two different biophysical emergent properties. The first one is going to be membrane fluidity, and the second one, in the next slide, is the membrane charge. So these two properties, I'm going to show you these two things are interrelated, of course, but also they are really interesting parameters that change the function of the cell surface and eventually the physiological responses of the cell. Next slide, please. Thank you. So let's first talk about membrane fluidity. So plasma membrane, generally cellular membranes, are made of lipids. This is the main constituents of the lipids. And this lipid structure actually determines what is going to be the fluidity of the membrane. If we have a lot of saturated lipids, then it becomes very ordered membrane, low fluidity membrane. And if you have unsaturated lipids, because of these double bonds that you have in the hydrocarbon chains, you cannot really pack the lipids tightly geometrically. That's why they have this high fluidity disordered membranes. And this parameter, membrane fluidity, is not really just a physical phenomenon. It is really an interesting and very physiologically relevant parameter because how the molecules diffuse in the membrane is determined by the fluidity. And this diffusion is basically determining how they will interact and how signaling happens. That is why it's really important to measure them. And how do we measure them? So this is going to be basically with the smart probes. Next slide, please. So with fluorescent probes would be the easiest way to measure membrane fluidity. And here there are some probes where we call them sometimes smart probes because whenever they go, wherever they go, they actually inform us about the environment. So for example, these probes that you can see, Lordan, difluanep, this kind of dyes, they go inside the membrane and they change their color depending on the environment. They become very redshifted in fluid environment, blue in very ordered, non-fluid environment. So when we use this dye and we check the color of the dye, we can actually quantify the fluidity of the cell. Next slide, please. So how can we measure this spectral change, the color change? We established this methodology, spectral imaging pipeline, basically to measure the spectrum of these dyes in an image, let's say in a T-REN cell, so that you can measure the fluidity of the cells in a slide, in a cover slip, for instance. Next slide, please. And then the problem would be, here you could show, by using this technology, that we could show many of the cellular processes are actually a parameter of membrane fluidity, starting from organelle function, metabolism, immunity. But again, we realized soon that if we want to measure millions of cells, many different cell types, live cells, this becomes very difficult in microscopy setup. Next slide, please. And that is why this live cell multiplex high throughput not possible in microscopy. That is why we decided to go for methodologies that could do this kind of measurements. Next slide, please. Thank you. And here, of course, immunology field already solved this problem. It is basically with flow cytometry, which is a single cell technology, really fast. We measure thousands of cells per second. But the main problem here would be flow cytometry is basically blind. Most flow cytometry tools, you don't see the image, you basically measure the signal. And if you want to measure the signal, you should be very sure where your probe localizes. In the next slide, what you're going to see is this very commonly used dyes, such as Lordan. They don't localize perfectly to one organelle. They localize the plasma membrane, but also all the internal membranes. So we don't know where the signal comes from. Do we measure plasma membrane fluidity or do we measure mitochondrial ER fluidity? We don't know. In the next slide, that is why we solved this problem by collaborating with the chemical biologists like here, I'm showing this dye Pro12A that we collaborated with Andrei Klemchenko from Strasbourg. And this dye is basically localized to a very specific organelle, such as plasma membrane. And of course, in the next slide, you could also see that we made these dyes different versions so that they would go inside different organelles, and they are still smart. So they don't only go to a place, a subcellular structure, but they still also give us information about the fluidity of that environment. So with this now, we can actually do high throughput biophysics because we know exactly where the signal comes from. Next slide, please. Next slide. So in the lab, we are interested in immunology, immune cells. How function of immune cells are parameters of fitness. Especially we want to understand how biophysical properties of immune cells change in different diseases, and if we can improve the function of immune cells by manipulating the biophysical properties. And that is why when we get this blood from different cohorts, we get this white blood cell part, PBMCs. And this PBMCs, you will see in the next slide, that there are many different cell types that you have probably heard of, from B cells, T cells, NK cells, dendritic cells. And all the cell types can be studied with one single antibody cocktail in flow cytometry. Each antibody recognizes a cell type, and each antibody has a different color. So whenever there's a color, let's say a blue color passes by, we know it's a B cell. And then if in this cocktail, we can add our smart probe, we can measure the fluidity of all the cell types at once. In the next slide, you will basically see how it looks like. So here you see 8 different cell types, 3 different smart probes, all with one single measurement. So we measure membrane fluidity, mitochondrial polarization, which tells us about the metabolic state, and membrane potential, which tells a bit about the charge. So now each dot here you see in this UMAP reduction in the dimensions, each dot is a cell, each cloud is a cell type. And what we learned from this cloud, so this is millions of cells, of course. In the next slide, you will see what we learned. So the first thing that we learned is cells assume different biophysical states. So if you look at, for instance, monocytes, dendritic cells, the x-axis, this delta GP axis, shows us the rigidity of the cells. Higher means less fluid, more rigid, and lower values means more fluid. You can see like monocytes, dendritic cells, they have a lot of different states, biophysical states, although surface-wise they look similar. With the markers that we use, with the antibodies that we use, they look similar. They are biophysically very different. Even homogeneous cell types like cytotoxic T cells, it's still a distribution. We never see a very sharp peak. There's always a distribution. If you look at the cytotoxic T cells, for instance, there are some cells sitting on 0.6 and some cells sitting on 0.8. And it's a very big difference in terms of membrane fluidity. And we ask the next question, is it just noise of the system, or a cell that sits on 0.6 is different than that cell sit on 0.8? Biophysically, they're different, but would functionally be they're different. And to address this, in the next slide, you will see that we developed a biophysical sorting methodology where we can sort the cells based on fluidity of the cells, for instance. So we can have a rigid cells, fluid cells from exactly the same donor. So we can do all the analysis that we can see what makes the cells different and if they are functionally different. So what we can do once we sort this, next slide, please. So we can do, for instance, downstream multiomics, which we did, for instance, transcriptomics. You will see in the next slide. If we compare all the transcriptomics of rigid versus fluid cells, you can see many transcripts changing. But then if you look at the pathways that change, for instance, chemotaxis, cell-cell adhesion, cell-cell interaction, this kind of stuff changes. This is really important. So these are NK cells, basically natural killer cells from a donor, from the same donors that have rigid or fluid plasma membrane. And from the transcriptome, we see that they might differ functionally, but we don't know yet. So these are just transcripts. One level above the transcript, we want to understand if the surface of these cells are different. That is why in the next slide, you will see the PixelGen analysis. So you will see from Hannah later how PixelGen works, but eventually it gives us 3 key parameters. So one is the abundance of this 155 proteins that you use in the PixelGen kit. Abundance is basically based on the abundance of the antibodies. Second is the polarity, which means if there is capping of the proteins, if they go from one side, if they're enriched in one side and not the other. This polarity is an interesting axis for immune cell activation. And third one is clustering and colocalization, which is also really interesting. We want to understand how different proteins cluster or colocalize with different proteins. So this is basically, if you think about colocalization, it's 155 proteins by 155 protein matrix. So it's very rich data. So if you look at the abundance, for instance, what we can see here, many proteins are higher or lower in fluid cells compared to rigid cells. Again, we are comparing exactly the same donors. So this is basically, so we don't have this genetic variability of person-to-person variability. It's basically we're comparing natural killer cells from donor 1, that is rigid, versus donor 1 in fluid cells. So a few things. So there's a very rich data, but what you can see here, for instance, fluid cells have more CD56 and less CD16. The CD markers, don't worry about this. This is I'll come to the important ones, but CD16 and CD56 are more or less giving us a sign that fluid cells might kill worse, because CD16 positive ones kill much better. CD16 negative ones kill much worse from the literature. Also, fluid cells have less integrin and adhesion molecules, so it might suggest that fluid cells also have low adhesion and maybe high motility. And then eventually we also have less glycosylated proteins in fluid cells, such as CD164, 162, Siglec-7, Siglec-9. There's a lot more data that is interesting for a lot of people, but for us, these three key messages are really important. So that is why we set out to understand a bit more on the surface architecture and the functionality of the cells. In the next slide, what you're going to see is this matrix that I mentioned, this colocalization matrix. So what here, again, you see a lot of proteins either colocalizing more or less in fluid cells versus rigid cells. While studying this matrix itself, every dot is probably a PhD project. But what is interesting for us, I'm going to get your attention to one single point, where ADAM10 and CD53. I'm going to talk about ADAM10 and CD53. In fluid cells, we see less ADAM10 and CD53 interactions. We'll come to this point, but in the next slide, what we tested that come out basically from the PixelGen analysis. If you go to the next slide, please. From the PixelGen analysis, we already inferred some of the functions, but we of course wanted to test this. So in the next slide, you will see two properties that we tested, two functional readouts. It's migration and killing. So when we see the migration, for instance, the fluid cells migrate faster while rigid cells kill better. Remember, from the PixelGen analysis, we showed that rigid cells have more CD16, so they would kill better, while fluid cells have less adhesion, probably they would get higher motility. So this is exactly what we have seen as well physiologically. So these biophysical differences, they already give us some functional output. We don't know exactly if this physical properties, such as membrane fluidity, directly involved in physiological responses. We are testing this in the next slide by applying, for instance, this 3D synapse properties, where we can see if the cells can form better synapses, depending as a, let's say, a function of fluidity, rigidity, and then if they kill differently. But at the moment, what we know is there are very good correlation. We can predict the fitness of the cells by looking at these biophysical properties of the cell. Next slide, please. So one property that I mentioned, that this ADAM10 and CD53, these are very vague terms, vague proteins now, but what we can see now, this fluid rigid pools. So there's basically an intermediate population where we can see of course, there are dead cells that we can label with annexin 5, and dead cells are very clear. They're really fluid, so we don't even see them at all. And then there's rigid cells, and the fluid cells in the middle, they also show the small PS, phosphatidylserine puncta, labeled by annexin 5. So annexin 5 is a protein that binds phosphatidylserine, which is a charged lipid that we're going to talk about now, that is about the membrane asymmetry, breaking the membrane asymmetry, which is shown in the next slide. So now we are talking about the membrane charge and charged lipids. Next slide, please. So when we look at the membrane, plasma membrane, there are a couple of things that we should remember. So first property I already told you about, membrane fluidity, saturation, unsaturation of the lipids. Cholesterol also affects a lot the fluidity. But also another really interesting collective property of the membrane is charge. So the charged lipids, we have negatively charged lipids and zwitterionic lipids, which is both negative and positive. And almost all zwitterionic lipids, the outer leaflet lipids are almost all zwitterionic, which means we don't have really a lot of charged lipids on the outer leaflet. Charged lipids such as phosphatidylserine and phosphatidylinositol, phosphatidic acid, these are all in the inner leaflet, almost exclusively. Where we know this, in the next slide, I could show you one paper from 73 and another paper in 2020 that we showed with collaborators, Leventhal Labs, that most negatively charged lipids, such as PS, PI, PG, they are in the inner leaflet. They don't go to the outer leaflet in a physiological setting where we can have normal healthy cells. So this PS asymmetry is really important because in the next slide, what you see is it is broken when the cells die, right? So when we know cells are dying, we use this annexin 5, even in assays, to see the dead cells, because dead cells, the asymmetry is broken, PS goes outside, and cell becomes completely negatively charged, so annexin binds. But it's not only true. I told you that in physiological cases, we don't have PS. That is completely untrue. In the next slide, I'll show you some examples where PS goes outside in a completely live system. Actually, PS flipping from inner leaflet to outer leaflet is really important for many cellular processes. It needs to happen so that, for instance, sperm fertilizes the egg. It is really important from starting of life all the way to some of the immune functions. So in the next slide, please. This PS asymmetry is ensured by enzymes such as flipases. So there's flipase such as TMEM30, for instance. This PS always goes outside during the cell cycle due to exocytosis, cell activation, but PS is always taken back inside. We don't want this PS outside by these flipases. Flipases take PS from outside to inside, so that outside becomes PS-free. And what happens when we don't have flipases? In the next slide, please. Well, when we have PS outside, these cells, in the literature, there was a consensus that we always considered PS positive cells as an eat me signal. Phagocytes eat PS positive cells, such as apoptotic cells. When cells go apoptotic, dead cells, we don't want dead cells around, so phagocytes come, clear them up. But recently, in the next slide, our collaborators show that this when there is mutations or knockout of the flipases, when flipases are gone, PS is supposed to be outside, so PS cannot be taken back in, so they become PS positive. But then these cells cannot be killed by natural killer cells. So there is a bit of a conundrum here. In one side in one hand, we are saying that macrophages and phagocytes, they really like PS positive cells. They immediately eat them. On the other hand, we are saying if the cells PS positive, they cannot be really killed by natural killer cells, for instance. So what is this conundrum coming from? In the next slide, please. So let's think about how a lipid can be a signal, an eat me signal or don't eat me signal. This is really interesting. This is a membrane for a cell biologist. Basically, it's just one line. If basically people respect a bit more the cell biology, in the next slide, you would see how we would think a membrane would look like. It's just two parallel lines. And in the next slide, you would see that your favorite protein in it, this would be a picture of the membrane that you would have. In this picture, it would make sense. If there's PS in the outer leaflet, cells could find this PS and eat the cells. But in the next slide, you will see probably more realistic cartoon of a cell. On top of this membrane, it is full of proteins and glycocalyx. It is such a crowded environment that I cannot really imagine a cell could come and see PS, which is a lipid that is underneath this forest. Imagine you are flying over a forest and you think that you're going to see a mice, and then basically see this, recognize this as mice, and then immediately go and kill this. So it's not very intuitive to think about that a lipid itself could be a signal. But how come that PS is an eat me signal then? Next slide, please. So that's why we asked this question. Can PS change the surface properties? It might not be itself an eat me, don't kill me signal, but maybe it can change properties of the cells by changing the protein composition, glycocalyx composition, so that we can see maybe that way PS regulates how immune cells interact or not. So with our collaborators, Quentin Satenter from Oxford and Berlin, recently we figured out how, for instance, in the next slide, you can see phagocytes, like macrophages, they eat apoptotic cells thanks to PS. Next slide explains the basic findings. So basically what Quentin's lab figured out that CD53, PSGL1, mucin1, very highly glycosylated tall proteins are shed from the apoptotic surface, while some of the proteins are not. So there's selective shedding of this big tall trees from the forest so that forest surface becomes more accessible. In the next slide, we basically have the model how it would be. Let's say in a healthy cell, we have forest completely intact. In this metalloproteases like ADAM10, they don't really cleave anything on the surface. And in the next slide, you will see when PS goes outside, such as in apoptotic scenario, part of this ADAM10 domain interacts with the PS, and it starts cleaving off all the proteins, the mucins from the surface. And when the mucins are gone, cells become more accessible by the phagocytes. That is how they can kill, and that clear, not kill, clear the apoptotic cells. So this shedding of big forest is really important, and ADAM10 is a big player in shedding the forest, and PS is a mechanism where ADAM10 can be activated. Well, we didn't know exactly how this would happen, this process would happen, but in the next slide, with our collaborators here in Stockholm, we actually did molecular dynamic simulations to see how ADAM10 interacts with membrane lipids, and we have seen that PS interacts with ADAM10, and in the next slide, we could show as we have more and more PS in the membrane, we go from one state, which is like a closed state, to a open state where it is probably catalytically active state where it can start shedding, chewing the proteins and then shedding part of the proteome from the surface. Well, now we have molecular understanding of how this happens. Next slide, please. We wanted to understand, this was with Quentin, for instance, we addressed with cell death, which is a bit invasive method to understand the role of PS, because with doing cell death, PS is not the only one that changes, right? So there are a lot of stuff changes. Do we really see the effect of PS externalization? So we want to do PS in live cells. It's some of the scenarios that I mentioned in physiological responses, physiological processes, there's PS going outside all the time. Next slide, please. So we want to do it in live, where we can mutate this TMEM30, for instance, which is a flippase. This flippase is taking the lipids from outside, the PS lipid from outside to inside, back to inside, so that cells become PS-free, surface becomes PS-free. But if you knock that out, then PS cannot go outside anymore. So you can basically have PS-positive cells. Our collaborators from Gothenburg, they showed this in the recent paper that this knockout cells, they're killed less by NK cells. And in another paper, it appeared in 2020, this mutations of TMEM30 is seen a lot in cancers, and this hematological malignancies are more prone to anti-CD47 therapy. They have shown that B cell receptor is more mobile. There was not mechanistic understanding, but it was really good correlation with tumor and the mutations of flippase. So in the first instance, in the next slide, you can see that we tested PS positivity of TMEM30 knockout. So you can see from different cell types, we can see, for instance, the PS knockouts are PS positive labeled with some PS binding proteins, while wild type is not really PS positive. In the next slide, you can see that when we did this analysis of fluidity, we measured the diffusion of some lipids on the membrane. You can see that knockouts are always more fluid. The membranes of knockout cells more fluid than the wild type. This correlation we have already seen from the previous story that I told you, where we see all this, we sort the cells based on fluidity, and we also see this PS puncta in the fluid cells. So fluidity and charge is probably PS exposure, and fluidity is probably related. So in the next slide, we also measured this membrane order with the smart probes that I mentioned. Knockout is always more fluid compared to wild type. And in the next slide, we did pixel gen analysis again. We understand now that lipids go outside, PS goes outside, and PS changes ADAM10, and then ADAM10 or some other metalloproteases, and then it starts remodeling the surface. So here what you see, for instance, again, in knockout cells where there's PS, we see less CD43, CD162. We'll come to these proteins, but more CD53, which I mentioned. There's CD53 ADAM10 that we have seen already, fluid versus rigid cells. There's more interaction in fluid cells. And there's a lot of other interesting proteins that I'm not going to cover today. But in the next slide, what I show, that we can also do polarity. I mentioned if proteins polarize to one side or the other, we could also see, now we can see also CD53 polarizing, not only more or less in wild type and knockout, but it's also more polarized, while CD162, CD43 is polarized less because they are less. So, but also we know now that how they are organized in the cell surface. And lastly, I'm showing you this matrix again, the colocalization matrix, that you can also see now some of the proteins like CD162 interactions changing. So this CD162 is again one of these big, large mucin domains. CD43, CD162, these are the ones that are changing the most. So now we think, even in the live condition, when PS goes out, it creates this, it remodels the surface. And to confirm this in the next slide, what we did, for instance, you can see with flow cytometry, we confirmed what we see with PixelGen with flow cytometry, that CD162, CD43, mucin 1 all goes down. They all go down in knockout cells. And we think this is PS driven, and PS activates ADAM family. And that is why in the next slide, we used an inhibitor for ADAM10 and ADAM17. When we use this GWGI, which is inhibitors of ADAM family, this loss of CD162, CD143, they were almost reversed. So we don't have any loss of these proteins from the surface in knockout, which means when we neutralize ADAM10, they don't cleave anymore the mucins. That is why we still have these mucins on the surface, even in the knockout cells. So with this, we confirmed that when PS goes outside, ADAMs get activated. And we already did the molecular dynamic simulation for the previous story, that we know exactly molecularly how it happens. And then now we know that they cleave off, ADAM family basically cleave off the mucins. Okay, next, please. So with this, I would like to conclude. So first of all, the cell surface lipids are quite important. So we always picture them as two parallel lines, but the diversity matters a lot, especially negatively charged lipids. When they go out, they activate some of the proteins like metalloproteases, and they cause major proteome changes on the surface, such as mutation setting. Next, please. And this PS and ADAM10 activity changing basically the surface architecture, maybe more accessible surface, more CD47 accessibility, more migratory phenotype. Next, please. And this is, at the moment, of course, we did these mutations of TMM30, but PS exposure is a lot more generic. It happens in almost every tissue during many cellular processes. That's why it's really important to see how these lipids transiently changing the cell surface properties cell surface proteome, interactome, proxiome, and how this changes the physiological properties. And lastly, in the next slide, please, I think we need to understand cell surface regulation is beyond central dogma. By doing transcriptomics, for instance, you cannot really understand how this PS going outside and then activating ADAM10 and then it sheds a lot of surface proteins. You cannot really understand seeing transcriptome. Even proteome, I would say, with the proteome, you would definitely get a list of proteins, but eventually how they interact, this is one of the central questions that we have now. How does lipids and biophysical properties change protein-protein interaction so that this changes the fitness of the cell, immune cell, and how this changes the response of the immune cells? That's why I think this is PixelGen technology became one of the critical technologies that we use now. Next slide, please. So with this, I'd like to thank my lab who do this work and all the collaborators all around the world. And thank you very much for hosting and looking forward to the discussion.
Thank you very much, Erdinch, for that tremendous talk. And yes, we're going to move into the discussion without any further delay. We're joined by Hannah van Ooyen from PixelGen's. She's PixelGen's Scientific Affairs Manager. Hannah, you've been waiting backstage patiently for the end of that lovely presentation. I know you've heard that or parts of that work several times. I'd love for you to give the audience just a sense of, from PixelGen's perspective, how does your technology, how has that played a role in furthering the kinds of research that we've just heard over the last 30 minutes?
Yeah, sure. Thank you very much. So really great to be here, and thanks a lot, Erdinch, for that presentation. And I think you really framed it well there at the end, that we are now, with all the kind of novel technologies being developed, our assay being one and your lipid probes being another, really showcasing that we're moving kind of beyond this central dogma, just looking at the level of transcripts or even the level of proteins that you have in the cells, and more fully understanding how they're regulated by looking at how they are interacting with each other, protein-protein interactions, protein-lipid interactions, all of these dynamic kind of changes in the protein organization. And this is really what we want to provide researchers with, technology that's enables you to look at protein-protein interactions and changes in organization. So those kind of features that you highlighted there, it's really something that we find very, very interesting and that I believe are part of many parts of biology. So you showcased a couple of examples now in some diseases, but it's going to be really, really interesting in the future to see the breadth of this alterations in the protein organization.
Erdinch sounds like a pretty satisfied customer from what I heard.
Yes, definitely. I think it filled a space that we definitely needed to be filled,
Right.
that we couldn't get with any other technologies. Yeah.
Right. We've had several questions come in, and they're coming in as we speak. So to the audience, please enter your questions in the Q&A box, and we'll go through them. Erdinch, what sheddase is involved in the PS change that you described?
Yeah, I think now major ones in immune cells, at least, is ADAM10 and ADAM17. But I think in other cell types will be very different ones that we are actually questioning at the moment. Also, this specificity, what changes is still under investigation for different cell types. Yeah.
I'm not sure I can maybe you can rephrase this a little bit, but will PS and influidity be influenced mutually?
Yes. So that is also a question that we didn't answer yet in the lab. So far, all the correlations show this way. So whenever PS goes outside, the cell membrane fluidity increases. So that is probably because a lot of physical aspects. It's related to tension, it's related to cholesterol content, it's related to the membrane acyl chain distribution of the lipid saturation inner versus outer leaflet. We don't know exactly what drives this, but whenever we see PS outside, we always see more fluid membranes. Yes.
I like this next question from Ruilin Yu. Wonderful talk. Can hard cells become fluid and vice versa? I'm amazed by how clear the two peaks for rigid and fluid cells separate from your biophysical facts
Mm.
instead of presenting as a continuum. Why do you think there are no
Yes.
cells with intermediate fluidity?
No, good question. It is actually intermediate fluidity. So there's one small peak on the very left-hand side that is actually dead cells. We don't talk about the dead cells at all. We just trash them. So the ones that we're talking about is the continuum. Some cell types, such as dendritic cells and monocytes, they have many different peaks, and they are peaks, but they are different states, probably different maturation state. But it's still a continuum. Some cells are bit like one single peak, but still a big variety in this continuum. Yes, this is definitely correct that we have a continuum.
Very good. Very perceptive question. Thank you. Urshad wants to know, do you think cell fluidity has any role in defective fetal development?
Oof, interesting question. I wouldn't know really, but I wouldn't be
Hmm.
surprised if there is. If you ask me, fluidity is the most important parameter in cell biology. So, well, my answer would be definitely yes.
Okay, well, I'm sure this evening or tomorrow you'll be hunting for collaborators in
Yes,
Karolinska to try to
yes.
address that question. That was a great one. Thank you. Besides PS, will calreticulin play a role in modifying
Mm,
fluidity versus rigidity?
yeah, we don't know, but also very interesting question, especially in the context of cell death and recognition of phagocytes. We don't know yet, but very good question, definitely.
Okay. Have you had a chance to look for changes in fluidity during cell differentiation?
Yes, that is a hard yes. So we not only differentiation from, let's say, from stem cell to different lineages, but also immune cell differentiation. We published a couple of papers with low throughput analysis, not with the flow cytometry tools, but with microscopy, spectral imaging. Last 5 years, I think we measured many differentiation paths that the
Mhm.
fluidity changes quite dramatically from one cell to another.
Mm. Greg asks, how do flipases get modulated to affect PS levels on the outer membrane?
Super good question. No idea. No idea.
That could be
Very
one
good
of the
question.
many, many PhD projects that you
Yes,
highlighted that your lab
yes,
can
yes, yes.
host.
I mean, this is a
Um,
fantastic question. I've been thinking about this in the last couple of months after actually PixelGen data. We got the PixelGen data, and I've been thinking about this. Like why cells don't want PS in the outer leaflet? Like what triggers flipases? Like, oh no, we don't want this. Like we have to get this back. And what is the thermodynamical mechanism that it knows that it should get the PS back inside? Very good
mm,
question, no answer from my side at least.
okay. Ertinch, just before we started broadcasting, you mentioned you have a couple of papers that you're excited about that are in press. I wonder if you would like to give the audience just a taste of when and where they can find some of your latest published research.
Yeah, I think they will be out in the next month, I would say. So we have three different stories that are coming up next month. So one will be TMM30A, how it regulates cell surface, and it will be out probably in the next month or two. And one story is a separate story that we developed this biophysical sorting and tried to figure out what this different fluidity means for the cell surface. And the last story is we applied this to cardiovascular disease cohort where we could see some of the cell types come as a biomarker. Um, and this will also be in the next couple of months, definitely out.
Mm, mm.
Mm.
Um, in the introduction to the webinar, in the abstract urgent, we mentioned that a lot of your research focuses on diseases like long COVID and certain types of leukemia.
Mm.
I'm wondering what other disease processes might really come into focus as your
Yeah,
research progresses.
yeah. So basically, we in the lab, my lab at least, we are interested in generally in inflammatory diseases, metabolic diseases, like diabetes, obesity, um, atherosclerosis, but also inflammatory disease like long COVID and some of the cancers, hematological cancers. But these are our focus. Since we develop tools, we also collaborate with a lot of other people to work on different aspects of cell biology and diseases. So we have a large focus on aging, resilience, and frailty. So what is the
Mm,
biophysical signature of
Mm.
resilience, for instance. This is basically what we are trying to figure out. We don't want to understand biophysical signatures of aging. Aging is something inevitable, but resilience, some individuals are more resilient than others. You know, when
Mm.
if you take 80 years old people, 80 years old people in Sweden, they still run half a marathon. Right? So we cannot really say they are same 80 years old compared to 80 years old people. They cannot even do shopping for themselves. Right? So we want to understand what makes these people resilient in terms of physical properties of immune cells, muscles, brain, and if we could manipulate this resilience state
Yes.
so that we could make immune cells more resilient for
Mm.
age population, so that we could get this healthy aging span a bit higher.
I mentioned that your lab is just a stone's throw from Pixelgen
Mm,
headquarters in Stockholm. And I'm wondering, as happy as you presented you are with Pixelgen's technology, is if you could give Pixelgen and maybe some other companies a wish list of reagents or
mm.
products or enhanced technologies that would really help your research turn the corner and move into some new areas. What are some of those things on your wish list?
Yeah, I think Hannah might be already Hannah and
Working on it?
her team may be tired of my suggestions
Ah,
because I all
Never.
I always go with like a wish list. So and
well, let's hear it. What's on it?
some of them are already implemented, I see. So I always wanted, for instance, like lipid probe, right? So I want to understand what is close proximity of my lipids, not only proteins, but then there's lipid binder proteins, right? So you might not have a very good antibody against lipids, but now they put this two custom protein, whatever you want, if you can get a good robust binding, so they could give 155 proteins plus two things that you are interested in that is not in this panel. And I'm really interested in lipids and some sugars. That is what I want to see. So this was one of this early wish list that I want my own stuff as well. So currently it's two. I think as the chemistry allows, it might be a bit more. Of course, we are for aging, especially, we are very much interested in intracellular targets.
Yes.
That was one of the wish lists, and of course, we want cheaper price, and every researcher would want, you know, this wish list generally. Um,
Yes.
that
You
a lot
you fo
more.
Erdinch, you focused on, I heard outer membrane many times. Do you look at
Mm.
other intracellular membranes as well?
Yeah, biophysically, definitely, we look at intracellular membranes.
Yeah.
Um, of course, when it comes to intracellular membranes, it's a lot more difficult to do all the other technologies, including Pixelgen, right? So it's at the moment it's surface
Yes.
restricted, and also any kind of flow cytometer. If we don't want to fix the cells for biophysical analysis, because if you fix the
Yes.
cells, you lose a lot of biophysical properties. So if you want to
Yes.
work with live cells, we are very much limited to
Mm.
outer membranes. But our probes that we develop, live cell probes, they go inside. They label the
Yes.
organelles as well. Yeah.
Very good. We're almost out of time, but I did want to bring Hannah back in and invite her to respond to anything. Either give Erding some good news about his wish list or respond to any of the other exchanges that we've heard over the last 10, 15 minutes.
Yeah, thank you very much. So obviously really keen to get the input from customers about what they wish us to develop next.
Yeah.
I hope you appreciate our improvements. We just launched this new product as Ernest mentioned, also an improved throughput, so you can now run 64 samples in one experiment. So it also helps for these kind of big clinical studies.
Yes.
So thanks a lot for hosting this webinar and letting Erdinch talk about his results.
Sure. We have another poll question that's just posted. I should have flagged those at the beginning, so my apologies, but I hope you've got time to respond to that. I don't see any other questions on the board, and we are just about out of time. So I think it's time to probably adjourn now. Plus, we have a very busy World Cup schedule to check out. My favorite time of the year. Thank you so much, everybody, for watching. Our thanks primarily to Erdinch Seglin, a PhD, for his wonderful presentation. That was really clear. Hannah, thank you, and Pixelgen for your contribution and sponsoring today's webinar. And I hope you get some nice feedback from some of the people who were watching. A quick programming note, Jen's next virtual spotlight is coming up on July 29th. That's just a few days before World RNA Day. It's on the subject of RNA therapeutics. Our special guest will be Nobel laureate Drew Weissman. That starts at noon Eastern time on Wednesday, July the 29th. The World Cup will be over by then, so you'll have plenty of time to go and watch it. On behalf of everybody at Gen and Pixelgen Technologies, thank you so much for watching this webinar. Goodbye for now.
Thank you.